session. Session 5. Okay. Well, first of all, of course, I would like to yes, seems to be the spot today. Okay. First of all, I would like, of course, to mention the people I did this work, this specific work I'm presenting today with, which are Antonello Provenzale, who is here, and mainly also Mara Baudena, who is not here today, but who actually did a lot, or most of the work for this particular topic. The topic of the talk is evapotranspiration fluxes. We have heard them mentioned quite often in these days. We have seen the patterns, we have seen the feedbacks which involve the patterns. We haven't spoken so much about the interaction between vegetation itself and the atmosphere. The atmosphere and the climate we have seen them appear usually as a forcing, but we actually know that there are important feedbacks between the two. These feedbacks, of course, occur at a wide range of scales. We can talk about the microscales. We have seen canopies in these past days. But there are also effects on very large scales, which can actually regulate and change, at least at the regional level, local climate. And then lead to actual feedbacks. There are a few examples which are quite well known. The most famous one is probably the Charney effect. Sorry. You really?
Just turn this microphone on.
Oh, that's a good.
Then you can go 2 ways.
Yes, thank you. A well-known one is the Charney effect, by which we have a positive interaction between the presence of vegetation and the climate through an albedo effect. So in drylands, you have vegetation which usually has a lower albedo than the surrounding soil. And this actually can lead to higher surface temperatures, to radiative effects. These higher surface temperatures then feed back on the atmosphere, can lead to more instability, which lead to more rainfall, which in turn leads to more water, and so we close the feedback loop. We can have also another example is feedbacks due to the transpiration itself, which is controlled by the vegetation. The transpiration fluxes from the vegetation will lead again to have effects on atmospheric stability. This has been actually also discussed recently in some papers. And again, on this case, also in this case, increase convection, precipitation, and so feedback on the vegetation system. These two specific examples can occur, of course, at a wide range of scales, but the Charney effect and also the second one also are thought to have this particular, well, actually more relevant at the regional scale. But then we talked in these days about completely different range of scales. We're talking mainly about vegetation patterns, and you have seen many of these pictures, but for example, this one, which is grass, here we're talking about the scale of tens of centimeters. And these are vegetation spots, and they are interspaced by these are shrubs taken directly from Google Earth. But also here we're talking about tens of meters, which is already much more than tens of centimeters. And but so in general, then we have another example of vegetation patterns, if we want to call them patterns, which we have seen, which is the discussion about the irregular patterns, or wide patterns characterized by wide distribution. So regardless if this can be considered a pattern or not, we can actually see from a simple distribution of sizes, which we see, which we have from the measurements, that, well, if you look at these graphs, the highest, well, here it's a bit very small, but this is expressed in meters, and the largest of these are again on the scale of hundreds of meters in a linear sense. So On the other hand, we know that these patterns are well distributed all over the world. This famous picture we all know about the distribution of drylands, and the classical, taken from one of these papers, which basically start all this interest into these patterns, and they're widely distributed over wide areas of the world, so that you might think they may play a role. We know, in addition, we know that it's not only the static pattern itself, of course, which has these characteristic scales, which are quite small compared to what we were mentioning in the first slide, but it's also the local, these scales directly derive from the local feedback processes which control the emergence of these patterns. I would already mentioned them, two examples, but of course there are many more, are the root feedback, and of course there you have the typical length scale, which is the length of the root system, the width of the root system. You have the infiltration feedback, but again, the infiltration feedback also due to the presence of sealing or of biogenic crusts, and the changes in infiltration due to the presence of vegetation. Again, these involve water movement over scales, which again of the order of tens of meters or hundreds of meters at most. So, and these patterns, on the other hand, these scales directly correspond to corresponding scales in terms of the evapotranspiration pattern of the vegetation itself. So we are directly led to what we could define the upscaling problem. The problem is that if we're interested in looking in the end, and this first part is basically a motivation, because then you will see I will go back to the small scales. We are led to the problem that if we were interested in, at a certain point, to study the effect of these feedbacks between the atmosphere and the soil-water system, we want at a certain point to go to very large scales. We may choose different methods to do this, but certainly one thing we know is that current models for the climate system, and which also include the effects of vegetation, they actually work on very large scales. I mean, the typical resolutions range between 20 to 100 kilometers. And this is very, very far from the scales we have just discussed. So this actually leads to the need, and I cannot fail to mention this paper by Max recently, which actually and many others actually, which widely discussed this issue, actually sort of discussed the problem, that actually we need to somehow to fill this gap. We have this problem. On one hand, we have models which work on a very large scale, and it's not reasonably possible at the moment, but probably will never be possible, to represent dynamically the small-scale dynamics of which at scales of 10 meters or even less, or centimeters, in a model where actually we are trying to resolve the global scales, and where we're limited by scales of order of 20 to 100 kilometers. So what is usually done is, of course, to parameterize what is happening at the small scales. So, but a parameterization immediately involves, and let me skip the next slide so we can see it here. The idea of a parameterization, of course, involves the idea that you need to use to describe the characteristics of the vegetation over your box, which has a limited resolution, using some properties which are bulk quantities. So we can use vegetation cover, we can use biomass, and we can go into as much detail as you want. But how do we insert into this the dynamics of the vegetation itself at very small scales? And we know that this may be relevant because, as we have seen, we have many examples of, and as we have already discussed, we have the issue of possible coexistence of different patterns. So at the same level of precipitation, at the same level, we may have different levels of the existence of patterns characterized by different levels of average biomass. We have coexistence of bands and spots, and these actually will correspond to different average bulk quantities in terms of biomass, in terms of fractional cover, and so on. And we know that this also translates directly into differences in terms of water. So in terms of, for example, of soil water. This is the same plot as before, but now looking at the soil water variable. And we have actually, also in this case, we have the possibility of coexistence of different soil water level states. And of course, the problem is then to translate this into parameterizations at larger scales. And this is soil water. What about the fluxes? What about transpiration fluxes? And in general, do these depend on the spatial configurations which the patterns, spatial configurations which a vegetation chooses, in particular in drylands? So this is basically the main motivation of what we are trying to address. And in order to do this, we need to go into more detail and look at the evapotranspiration related to the pattern formation phenomena we have been seeing these days. But there's an issue about that, which is, well, I would just mention that we need at a certain point possibly to complicate our models. In fact, as soon as you try and do that with some of the models we have been using for some years now, you realize that you actually need to do this. So you need to make the model more complicated, because actually, so one aspect which has been already explored partially is the fact that, of course, in drylands, precipitation is not a constant average precipitation, but is actually characterized by a strong intermittency, so by a specific distribution of precipitation during the year. This leads more to a sequence of precipitation episodes rather than having precipitation as a single variable which controls the system. Then we have to take into account the fact that actually evaporation, it can be quite rapid from a thin top soil layer. This is another aspect which at least we have neglected up to now. But then it will not occur from the deepest soil layers. So a model like the Gillard et al. Model, which myself I have been using for years, considers only one soil water level. And it so cannot, of course, capture this specific effect. And on the other hand, the evapotranspirative fluxes will be important or will be relevant after precipitation events. They won't be very strong after a long time when actually the top layer has dried up, and you are left mainly with the transpiration of the from the plants. So what we want to do is actually to separate the evaporation from the transpiration. So in order, so here we have a little scheme of how we could actually make our model slightly more realistic. So I'm going now to present this two-layer model and then show you some of the results which this model shows in terms of evapotranspirative fluxes. So instead now of having one single soil water level, we actually split it into two levels. We have one level which is a root zone level, and we have a thin top level of much less, of 5 or 10 centimeters. Evaporation now, we make it occur mainly from, or only from this top level. Infiltration, of course, occurs first in the top level. Then if that level saturates, it moves down to the root zone level. And transpiration instead, of course, occurs through the vegetation and through the root system from the second level. And then we have a deeper level, which is just represented here, which of course is not reserved, is simply a sink for leakage from the root zone level. So to go into more detail, this is a modified model. this is a modified model. It has basically all the elements which we are accustomed to. So we have a biomass equation, we have a land surface runoff variable, and then now we have actually two variables for soil moisture. And the evaporation occurs only from the first one. And as I said, we have an infiltration term, which actually, and leakage term from the first layer to the second one, which becomes a source term for the second soil layer, and from which the root uptake occurs. So, translating this into the actual equations, you can recognize a similarity to the equations which I would just showed. In fact, it is a modification of the same model. So nothing has changed for what relates to the surface runoff. But the main change is that now evaporation is only here. We have a leakage term. We can choose different functional forms. Maybe I can go to this slide where we can show more the details. Different functional forms can be chosen for that. The main point here is that now infiltration, infiltration is the same as before. The main point here is that we have to control what happens with the top layer when that saturates. So there we chose to go to the time scale of the single rainfall event to check if the top layer saturates, and the excess water then is made to infiltrate actually to the lower level. The same process in theory can occur also for the root zone level, root zone layer, but of course this requires very high precipitation levels, so that rarely occurs, at least in the parameter ranges which we explored. Then the other elements, I don't go into much detail because basically they have already been discussed. Well, the main point which we may again mention is that in this model, as I would just said, we have the root uptake part, which is actually controlled by an integral equation. So, and this is, will be actually be an important point in a short time, namely that we have the vegetation at one point actually picks up water from its surroundings. Well, then final detail, since surface runoff is very fast compared to the other time scales, we can actually neglect the time derivative for the surface water equation and actually solve this equation as an implicit equation, but this is a technical detail. So what happens when we apply this modified two-layer model? Well, the good news is that, of course, using a realistic parameter range, we are still able to get the usual sequence of universal patterns, but this, as we now know, we shouldn't be too surprised about. But the good thing is that we also get similar effects of bistability and coexistence of the patterns. And the good thing, though, is that if we try and attempt a comparison of these results, also in terms of the transpiration and evaporation fluxes now, using this model with observed data, well, we find some quite decent agreement. There are not too many data to compare with, or actually there are plenty of data to compare with. Here we chose actually one particular quite famous set of experimental data. And what is particularly good here is that this comparison fits quite well without actually tuning the model in any sense. We chose realistic and reasonable parameters for that precipitation range, and we immediately, and for that type of vegetation, we immediately got reasonable results and reasonable agreement. Reasonable agreement both in terms of evapotranspiration from the dry areas. Say again? Sorry?
Go ahead.
And from the non-vegetated areas and from the vegetated areas. we have the bistability of patterns. We have the bistability in terms of biomass density and of vegetative fraction. So now what about the transpirative and evaporative fluxes? Do they also show a similar behavior? Here we have to take into account another aspect, which is the fact that models like this typically, or at least in this case, since we did not include explicitly the role of topography, they represent sort of a closed system. What comes in terms of precipitation needs at a certain point to come out. And so, of course, there's a total balance between the precipitation coming in and the transpiration and evaporation coming out. Of course, the only sources of leakage are represented by possible deep leakage to the deep layer. But this is actually quite reduced, since this is actually this only occurs briefly after a precipitation event, and overall we can find out that this is not, at least, it's not a too relevant term. So what happens? So what we should actually look at is what happens immediately after precipitation event, and if we do that. So what we represent here is actually averaging transpiration and evaporation in the 5 days following a precipitation event. So what we find here, after doing a very long transient and actually averaging over hundreds of years of model run. So, well, here we find the bistability of the evaporation. We apparently do not find too much differences in transpiration, and we find very similar levels in soil water levels, both in the top thin layer and in the deep layer. We actually have to consider, though, that the biomass densities of these two types of patterns are different, as we have seen. So it's probably more instructive to look at these plots if we normalize by the fraction of area covered and normalize per unit biomass. And if we do this exercise, we actually see quite nicely, this is transpiration normalized so transpiration per unit biomass. And whereas here it's transpiration per unit vegetated area, and we have evaporation per unit bare soil. And so here we find that evaporation per unit bare soil actually does not change significantly. Whereas we have two coexisting states of transpiration corresponding to the different patterns. The top line is for spots, the lower line is for bands. And this, the differences are not big, the 10–15%, but the main point is that the pattern geometry now we see plays actually a role. So the fact that the pattern geometry plays a role is actually linked to the mechanisms of local feedback and competition which we put into the model, mainly to the, in this case, to the root zone feedback. If you think of a single spot, it actually will have less competition from surrounding spots compared to a band. A band can actually take water only from two sides, but it will feel the effect of other vegetation around it in the other direction. So, so this explains why there should be, at the same level of average biomass, why there could be a difference in terms of transpiration between a spot pattern and the banded pattern. On the other hand, evaporation is a purely local phenomenon in our local phenomenon, and so we do not expect that there will be any differences. It will only depend on the fraction of area covered. So there I go now to the second point, which we can explore with this model, which is actually difference? Will there be a difference if we let the system evolve naturally, or if we actually impose the pattern? So it could be if we choose or change the surface in order to impose a pattern naturally, or we're trying to do agriculture. So if we, let's assume we take the model, we evolve dynamically a pattern, having chosen a certain length scale for the size of our box, so in this case 3.75 meters. Now we do the following exercise. We keep this pattern fixed, and we actually rescale it. So we move it to be a box of only 2 meters side or a box of 6 meters inside. What I want you to notice is that actually the fraction of area covered by definition does not change if we do this exercise. And we just rescaled the box. So also the shape of the patterns only changes in terms of length scale. The main difference is that this, of course, is not the pattern which the model would have chosen had it been run naturally at that scale. So, so if we do this exercise, and we can then again go and look what happens to our soil water, to our evaporation and transpiration. Well, evaporation, we shouldn't be too surprised because, as we said, it's a purely local phenomenon. So apart from a little difference at small scales, which is actually related to water diffusion and close to the patches, we do not see any difference as a function of the main size. The little cross actually indicates the scale which we actually chose where the pattern could actually be chosen dynamically. What we see is actually a difference in terms of transpiration and particularly of soil water. So what you see is that actually if we go from our chosen size, which was actually chosen by itself by where the pattern was chosen by itself by the model, and we reduce the scale of the system, we see that soil water actually slightly increases. And this can be linked, this actually is linked to, and we have tested this, this is actually linked to the presence of a soil water diffusion term in the equations. And so particularly what is increasing is the soil water in the bare areas. So the dashed line represents the bare areas, the continuous line actually represents the statistics done only over the vegetated areas. On the other hand, when we increase the scale, what we see is that the water in the bare areas increases dramatically. And this we can understand if you think that, well, each patch actually collects water through the root system at a given length scale from the surrounding area. If we simply increase the scale of the system, not having actually changed anything else in the model, so we actually didn't change this root length scale, of course, each patch will fish water only from a reduced part of the bare area, leaving large parts of the bare area where the plants do not actually collect enough water from. This actually leads from a reduction to a reduction of the water collected through the roots and then ultimately by transpiration from the bare areas, and explains why the water in the bare areas actually increases. On the other hand, and I believe this cartoon will show this better, we will have an increase of transpiration from the vegetated areas. You can see that here in this line. And this can be illustrated as a simple cartoon, but where again, I will now plot the idealized patches from idealized areas from which a single individual plant collects water from its surrounding. So I can fill this up with little circles. So the little points are idealized plants sitting at that point. Each one collects water from its surrounding. And now we go to a much larger patch. And what you notice is that actually the number of individuals sitting on the border, since the border grows linearly and the area grows with a square of the size, become less and less compared to those sitting in the inside. And since after a precipitation event, due to the infiltration feedback effect, water is particularly available where vegetation is, this allows higher transpiration if the patch size is larger. So we have these two competing effects, that we have increasing transpiration from vegetated areas. We have a reduced pickup of water from the bare areas. And this actually leads, as we can see in terms of the average soil water overall, over the whole domain, to a minimization, or at least to a minimum of water exactly at the scale which we had chosen to be where we let the pattern develop naturally. So this is my last slide. If we repeat this exercise to make sure that this was not an accident of the particular scale we chose initially, we can repeat this exercise for different scales, for different box sizes. So we choose different possible box sizes, let the pattern evolve naturally, and then repeat this exercise of keeping vegetation fixed, but rescaling the pattern. And if we do that, we get these different curves. So this 4-meter line is similar to the curve we had before. It's basically the same. And these other lines are curves obtained, again, in terms of soil water, obtained at different scales. And what I would like you to notice is that the minimum of these curves always occurs at the scale, which is actually the scale of where the pattern could actually develop naturally. So, so to answer the second question, what occurs if we actually force a pattern to live at a scale which is not the scale it would have chosen naturally, we find that actually a phenomenon of by which soil water is actually minimized. So, and these are my conclusions. This is just the first step, of course, so I didn't even address start addressing the issues which I summarized in my motivation, but it's a first step. So we need first to get a model where we have a more realistic treatment of transpiration and evaporation, and mainly a model where we can actually separate the two more clearly, and so that and we find actually that the main point is that we actually find that there is an effect of the pattern states on the transpiration. And this actually means that even if it's not much in our case, 10%, you may argue that that is not too relevant. But by the principle, the idea is that since this is occurring, we may have to take into account the pattern dynamics when we consider the coupling between the soil, vegetation, and the atmosphere. Since we know that the pattern dynamics can lead to bistability, we have related this, we have discussed critical state, we have discussed critical shifts, hysteresis. So all these also will apply to the transpiration. And yeah, and then we also have seen that the self-consistent vegetation patterns actually lead to the minimum of soil moisture in the bare soil, and this is actually a point which is which can be explored if it's a curiosity, but I would say it's actually just an indication of how the vegetation, of course, is choosing. I wouldn't say to optimize, but it's choosing to exploit to the last bit the resources it has available. And yeah, thank you.
Okay, thank you. Time for one very urgent question. In short. Yes.
Just to follow up to the previous questions, now you diffuse even surface water, and I don't know if this is something that has any physical basis. Basically, you in your equations, not only you diffuse the soil moisture, but you also diffuse the surface water.
Okay, no, well, this is an old topic, you know, between. I mean, we already discussed this in Valsavaranche.
And I don't remember the answer, honestly. Yeah.
The main point is that we need a mechanism in the models to represent surface transport. You can do it in a very complicated way, or you can do it in try to do it in a possibly simple way. The detail of how you do it actually will not change the point, as Ozeud was pointing out, that you need to move the water in order to then have the infiltration feedback. And how you move the water laterally, the detail of that will be not too relevant. We actually, let's see if I have it here, we have, let's see if I have it yet. We have here, you see, we have an h squared. We have no nabla, we don't have nabla h, nabla squared h, we have nabla squared h squared. But this, you can motivate by deriving it from a more realistic equation, but it's a debate.
I think we should
choose it, you can change it.
Close it here. Okay. Just the short answer is the shallow water approximation in the lubrication approximation. Shallow water, you can get it from Navier-Stokes.
Yes, but it's not the point. I mean,
it's not the point.
You could also get it to put,
So, thank you. AZ. So you have 5 minutes.